Hi guys, welcome to enginerdmath channel. We're live. Our topic for today is about inverse trigonometric functions of complex numbers. So by the way, I already have previous videos all about complex numbers like operations on complex numbers such as addition, subtraction, multiplication, division of complex numbers in rectangular form, simplifying powers of imaginary number I, transforming or converting complex numbers in rectangular form to polar form or exponential form and vice versa. Operations of complex numbers in rectangular, polar, and exponential form. Powers and roots of complex numbers. Exponential functions of complex number to the base e. Logarithm of natural logarithm of complex numbers. Logarithm of complex number to another complex number base. Complex number raised to complex number, trigonometric functions of complex number, inverse trigonometric functions of complex number, and hyperbolic functions of complex numbers. So if you haven't watched them yet, I will just put the links of the description of all those videos so you can check them first. Remember, if it's important you have watched them all before we proceed with the current lesson because everything that we've discussed there will be applied here. Okay, so now we will proceed with new topic which is the inverse hyperbolic. Let's change this. Let me edit this. It's not trigonometric anymore, but it's hyperbolic. Okay. So when evaluating inverse hyperbolic functions of complex numbers, you must memorize this formula. So we have 6 corresponding to the inverse of the 6 hyperbolic functions. The sinh, the cosh, the tanh, the cosec, the sec, and the coth. Okay, for the inverse hyperbolic sine or arcsinh z, it is equal to ln of z plus the square root of 1 plus z squared. For the inverse of hyperbolic cosine z or arc cos z, it is equal to ln of z plus square root of z squared minus 1. For the inverse of hyperbolic tangent z or arc tanh z, it is equal to 1 half ln of 1 plus z over 1 minus z. For the inverse of hyperbolic cosecant of z or arc cos z, cosec z, it is equal to ln of 1 plus square root of z squared plus 1 over z. For the inverse hyperbolic secant z or arcsec z, it is equal to ln of 1 plus square root of 1 minus z squared over z. And for the inverse of hyperbolic cotangent z or arccoth z, it is equal to 1 half ln of z plus 1 over z minus 1. So all you need to do is to memorize this formula and then evaluate each expression to find the final value of the inverse hyperbolic functions of complex number z. So what do you notice? Just like in inverse trigonometric functions, we involve ln in all the formula, meaning all of these inverse hyperbolic functions of complex numbers are multivalued. So we will find both the principal value and the general values. Also, particularly for arcsinh, arccosh, arccosec, and arcsec of z, in the formula, they have square root. Okay, so therefore, because of the Moivre's theorem in evaluating square root, we must have two sets of answer for them. Okay? So now, to illustrate how to evaluate inverse hyperbolic functions of complex numbers, let's solve some examples. Evaluate the following complex numbers. For number 1, what if we have arcsinh arcsin of 2 plus 3i. Okay, so we will apply the formula. Arcsin of z is equal to ln of z plus square root of 1 plus z squared. So arcsin of z is equal to ln of z plus the square root of 1 plus z squared, or it can be z squared plus 1 also. Okay? Wherein your z here is this complex number 2 plus 3i. So substituting the value, arcsin of z 2 plus 3i is equal to ln of z, which is 2 plus 3i, plus the square root of 1 plus z squared, which is 2 plus 3i. So we have 2 plus 3i quantity squared. Then we simplify first the expression inside this square root. So we expand the square of the binomial. We have 1 plus squaring this 2 plus 3i. So the special product for square of a binomial, square the first. That will be 4. 2 square is 4. Plus the product of the first and the second, 2 times 3i, 6i. Multiply it further by 2. 2 times 6i, that's 12i. Then plus the square of the second term, 3i quantity square, that will be 9i squared. Okay? And then we can simplify further inside the square root. So we have ln 2 plus 3i plus the square root. So you can actually remove the parentheses because the operation before the square of a binomial is just addition, right? So we can combine 1 plus 4, 5, then plus 12i. Then 9 times, we know that I square is negative 1. Therefore, positive 9 times negative 1, this will become negative 9. Okay, and finally, we can still combine 5 minus 9, negative 4, plus 12i. So next is to evaluate the square root of negative 4 plus 12i. So here we will apply the Moivre's theorem for roots of complex number. I already have previous video about that with title powers and roots of complex numbers. So you just check it in the link. It is in the description if you want to watch it. So we will start for the square root of negative 4 plus 12i. So we will convert first this rectangular form, negative 4 plus 12i, to polar form. So identify the x, it is negative 4. Identify the y, it is 12. So what quadrant does the complex number lie in? It is x negative. For x, it's negative. For y, it's positive. So therefore, it is in quadrant 2. Okay? Then, for the formula for r, it is the square root of x squared plus y squared. Substitute the value. X is negative 4. Then we square. Plus y is 12. Then we square. Simplifying, square root of negative 4 quantity square, that's 16. Plus 12 square, that's 144. So adding 16 plus 144, that will be 160, right? You can also simplify square root of 162 for square root of 10, right? So this is the modulus R for square root of 10. How about for the theta or the argument? If the complex number is in quadrant 2, formula for theta is arctangent y over x plus pi, right? Substituting the value, we have arctan of y, which is 12, divided by x negative 4 plus pi. So you can use your calculator. So input this arctan. Make sure that your calculator is in radian mode R. Okay. So shift setup 4. So we will have arctan of 12 over negative 4 plus pi. So approximately 1.893 rad in 3 decimal place. Next, so now that we have the modulus and the theta, we can now apply the de Moivre's theorem for roots of complex number. Therefore, square root of negative 4 plus 12i is equal to the square root of the modulus r, which is 4 square root of 10, then angle of the theta argument 1.893 plus 2 pi k over the n2. So the n here, or the index, is 2. Invisible 2 if the index, or if the radical or the root is square root, right? Okay. And this will run for values of k, 0, and 1. So that we will have two corresponding square root of negative 4 plus 12i when we set first k 0, and then when we set k next is equal to 1. So we will find first the principal square root. We can have that by setting k equal to 0. So therefore, the square root of negative 4 plus 12i is, so square root of 4, square root of 10, angle of 1.893 plus 2 pi k, you substitute 0 with k over 2. Or you can just remove this term since it's just equal to 0. So what you will have is just square root of 4, square root of 10, angle of, you can divide 1.893 by 2. Okay, 1.893 divided by 2. So that's 0.9465. 0.9465. You can also write this in polar trigonometric form. It is also equal to the square root of 10 cosine of this theta 0.9465 plus I sine of same theta 0.9465. So to convert this in rectangular form, you can use your calculator. You can input this, or the easier way is to just input this R angle theta form of complex number in your calculator. So put the mode of your calculator in complex. So press mode and then select 2 for complex. And also, don't forget to put your calculator, the angle, in radian mode, which you already have put it already in radian mode. So shift setup 4. So you just input square root of 4, square root of 10, and then angle 0.9. Sorry. The angle should be outside the radical. So you just press right button and then shift angle, then 0.9465. So you can get the approximate rectangular form 2.079 plus 2.886i. Okay. And then we plug in this value of square root for the formula for arcsinc, this one. Okay. So this is the formula for arcsinc of 2 plus 3i, right? So we can now have approximately equal to ln 2 plus 3i plus this approximate value of the square root, the first square root that we consider when k is 0. Let's just copy here. Okay, and then we add this complex number with this 2 plus 3i. So you can just input in your calculator, or it's easy to add because they are all both positive, right? You just combine. So ln of 2 plus 2.079 for the real parts, that will be 4.079. How about for the imaginary parts, we have 3i plus 2.886i, that will be 5.886i. Okay, and then we need to evaluate this ln of this complex number in rectangular form. So how? Okay, you can watch my video. Topic or title is Natural Logarithm of Complex Number. It is linked on the description. If you want to watch or if you haven't watched that yet, so that you will know the steps clearly how to evaluate the ln of complex number. But we will show it again here. So how? You convert first this complex number in, this is in rectangular form, convert this to polar. Okay. So, x is 4.079, then y is 5.886. So, what quadrant? Both x and y are positive, therefore, it is in quadrant 1. So, r is equal to the square root of x squared plus y squared. Substitute the value of x, that's 4.079 squared, plus y is 5.886 squared. You can use your calculator. Input square root of 4.079 square plus 5.886 square, and you will get approximately 7.161 for the modulus r. And then for the theta, if the complex number z is in quadrant 1, the formula for theta is arctan of y over x, right? So substituting the values of y, we have this one, 5.886 over x, we have 4.079. Again, input in your calculator, you have arctangent of 5.886 over 4.079, and you will get approximately 0.965 rad. Or by the way, I haven't shown you even in this step. You can also convert complex number using your calculator. Just input -4 plus 12i. You can convert complex number in rectangular form to polar form, using your calculator. Just input the complex number in rectangular form, and let us check if we will get the same answer. Once we use our calculator to convert this -4 plus 12i to polar form, so just input first -4 plus 12i, and then press shift 2 complex and then 3 for our angle theta form equal. So see, we also got r, which is 4 square root of 10, and theta approximately 1.893 as well. Also, here, we will try to check using the calculator. Let's convert 4.079 plus 5.886i to polar form. So, input 4.079 plus 5.886i equal. Then again, shift to 3 equal. So, we will get the approximate value of modulus r, same, 71.161. And the angle theta, same, approximately 0.965. Okay, now that we have the r and the theta, we are now ready to evaluate the ln of this complex number. Applying the formula, it is now approximately equal to ln of the modulus r plus I argument theta. Substitute the value ln r, which is 7.161 plus I theta, which is 0.965. Using your calculator, approximate this ln of 7.161. It is equal to 1.969, 3 decimal place, plus 0.965i. Okay, so this is your actually, this is already the answer for the arcsinch because this is the last function that we will evaluate. This is the principal value of the ln, or in short, PV, and it is also the principal value of the arcsinch. Remember, ln is multi-valued. You can have the principal value and the general value. So since arcsinch involves ln in the formula, arcsinch is also a multi-valued function, right? So you can get a principal value and a general value. Now, we can also get the general value of this ln. So ln of 4, or let's just copy. So ln of 4.079 plus 5.886i, its general value, so same, almost the same. So you just copy 1.969 plus 0.965, but you must always add multiple of 2 pi. So you must always add plus 2 pi n and then times the I. So this will be the general value. Or for short, let's call it GV. And this is true for all integers n. So that n can have 0, plus minus 1, plus minus 2, and so on values. Okay? So this is already the answer for the arcsinch, the general value for the arcsinch. Okay, and this is the principal value for the arcsinch. Okay, and then we're not yet done because, like what I've said, since we involve square root in the formula, we require to have two values for that square root. The one that we got was when k is 0, so we must find also the value of the square root when we set k equal to 1. So we can basically copy the same formula, but now, instead of setting k equal to 0, we set k equal to 1. Okay? For the second square root of negative 4 plus 12i. Therefore, square root of negative 4 plus 12i is now equal to square root of 4 square root of 10 angle of 1.893 plus 2 pi k, substitute k is equal to 1 over 2. So that it is equal to the square root of 4 square root of 10 angle of, you can input this in your calculator. You will have 1.893 plus 2 pi times 1, or simply 2 pi over 2, which is approximately 4.088. 4.088. Okay? So this is also equivalent in polar trigonometric form to 4 square root of 10 cosine of 4.088 plus I sine 4.088. So in rectangular form, it's approximately equal to, when you input this in your calculator, you will have 4 square root of 10, square root of 4 square root of 10, right? And then angle, okay, angle of 4.088. Approximately negative 2.079, then minus 2.886i. Okay? So you must substitute this again in the formula for arcsinch here. So arc sinh of 2 plus 3i. So it's now approximately equal to ln of 2 plus 3i plus this is square root when k is 1. This is the approximate value. You can just copy. Okay. And then you combine this complex number. So you can use your calculator since it involves decimal now. Just input 2 plus 3i plus negative of 2.079 minus 2.886i equal, in decimal, it is negative 0.079 plus 0.114i. Okay, and then we evaluate this ln. Doing the same steps, convert this to polar form. So your x is negative 0.079. Your y is 0.114. Therefore, what quadrant? X is negative, y is positive. Quadrant 2. So the value of r, square root of x squared plus y squared. Substitute x, it's negative 0.079 squared plus y, it's 0.114 squared. Using your calculator, so square root of negative 0.079 squared plus 0.114 squared. It's approximately 0.139. Okay. And then for your theta, if your complex number is in quadrant 2, again, the formula for theta is arctan y over x plus pi. Substitute the value, we have arctan y 0.114 over x negative 0.079, then plus pi. Input that in your calculator, arctan of 0.114 divided by negative 0.079 plus pi. It is approximately equal to 2.177 rad. Again, if you try to convert this directly using your calculator to polar form, just input this complex number, negative 0.079 plus 0.114i equal. Then press shift to 3. Okay, you will see you have the same r, 0.139, and same theta, 2.177 rad. Okay, now we evaluate this ln applying the formula. Ln of this complex number is equivalently approximately equal to ln of r 0.139 plus I of this theta 2.177. So using your calculator, ln of 0.139, it's approximately negative 1.973, then plus 2.177i. Again, this is the principal value of your ln and also the principal value of your arcsin. The final answer already. Okay. You can also have the general value. Okay, the general value for this ln is the same. So just copy negative 1.973 plus 2.177 plus, but you must always add 2 pi n, then quantity times I. This is the general value for integers n. So n can have values of 0, plus minus 1, plus minus 2, and so on. So this is the general value of the arcsin. Okay, so we have two sets of answers. This one, general value, principal value, and the first set of answers, this one, general value and principal value for arcsinch. So how do you check it using your calculator? You can just input this in your calculator. You can start with this expression. Once you have substituted all the z, okay, always start with the expression inside the square root. So input 1 plus 2 plus 3i quantity squared. So 1 plus 2 plus 3i squared. Okay. Since we're trying to get the square root, okay, input square root, then shift abs of the ans, and then angle of the argument. So shift to 1 of the ans. If we try to find the value of square root using k equal to 0, you will have plus 2 pi times 0, right? In the formula, this one here. Over 2, then equal. Okay, so this is the principal square root for this expression. Okay, and then you need to add with 2 plus 3i, so plus quantity 2 plus 3i equal. So this is now the sum of this. This expression is now equivalent to this. Then you try to get the ln of this. So how? Just input ln of shift abs of the ans, then plus I shift to 1 of the ans equal. So this will be the answer. Let's check. Okay. Approximately 1.969 for the real part plus 0.965i for the imaginary part. So we're correct to three decimal places. Okay? This is the exact value of the complex number. Okay? When you try to input in the calculator. Next, how about for the second set of answers? So same, you will start with this expression. Start with this one. Again, input 1 plus quantity 2 plus 3i squared. Okay, and then get the square root of this. So square root of abs of the ans, angle of argument of the ans. So shift to 1 ans. But this time, we set k to 1. So we must add 2 pi times 1 over 2, right? Okay, so this is the square root of this complex number when k is 1. You add it again with 2 plus 3i, so plus 2 plus 3i. Okay, so this is now the value of the of the expression inside the ln, this one. Then you get the ln. So ln of the absolute value of the ans plus I shift to 1 argument of the ans equal. So let's check if we got the same answer for the second set of solution. Okay, we got approximately negative 1.973. Okay, but on the solution of the calculator or the answer in the calculator, it's negative 1.968. So there is a discrepancy due to the rounding off in every step of this solution, right? But if you approximate this to approximately in to the nearest one digit, one decimal place, I mean, they are approximately equal, right? How about for the real part, imaginary part, I mean, 2.177. Okay, so it's quite close for the imaginary part. 2.177, approximately the same up to 3 decimal place. Okay? So that's how to check your answer using your calculator. Okay, next. Number 2. What if r cosh of negative 7 plus 5i? So looking back at the formula for r cosh z is ln of z plus square root of c squared minus 1. So r cosh of z is equal to ln of z plus the square root of z squared minus 1, wherein the value of z is negative 7 plus 5i. If you substitute the value of c, we will have r cosh of negative 7 plus 5i equal to ln of c, negative 7 plus 5i, plus the square root of c, negative 7 plus 5i squared minus 1. Again, we start simplifying the expression inside the square root. So, expand the square of the binomial. Square the first, negative 7 quantity squared, that's positive 49. The product of the first and the second term, negative 7 times 5i, that's negative 35i, times 2, negative 70i, right? Plus the square of the second term, 5i. 5i quantity squared, that's positive 25i squared, minus 1. ln of negative 7 plus 5i plus the square root. So, combine similar terms. 49 minus 1, 48, minus 70i, plus 25i squared, that's negative 1. So, that 25 times negative 1 is negative 25. Okay. Then, finally, we can add 48 or combine 48 minus 25. That will be 23 minus 70i. Again, we will start evaluating the square root of this 23 minus 70i. So, for the square root of 23 minus 70i, again, convert this to polar form. So, x is 23, y is negative 70. So, x is positive, y is negative. The complex number is in quadrant 4. R is square root of x squared plus y squared. So, square root of 23 square plus y negative 70 square. So, it's equal to, using our calculator, square root of 23 square plus 70 square, a negative 70 square. But actually, it should also be the same, because once you square the negative, it will be positive. So, approximately 73.682. Okay. For the theta, formula for theta in quadrant 4 is arctan y over x, right? Substitute arctan of y is negative 70 over x 23. Use your calculator. Arctan of negative 70 over 23, approximately negative 1.253 rad. Okay, or you can directly input in your calculator 23 minus 70i, then shift to 3. It will be converted to polar form as, so same R, 73.682 And same argument theta, negative 1.253. Therefore, using the Moivre's theorem, the square root of 23 minus 70i is equal now to the square root of r, which is 73.682, then angle theta, negative 1.253 plus 2 pi k over 2. For k is 0 and 1. So let's start for k is equal to 0. So square root of 23 minus 70i is square root of 73.682 angle of negative 1.253 plus 2 pi k, substitute 0, over 2. So that approximately it is equal to the square root of 73.682 angle. So this is the 0. No need to add this. Just input in your calculator, negative 1.253 over 2. So negative 1.253 over 2, it's negative 0.6265. Negative 0.6265. Okay, it is also equal in polar trigonometric form to square root of 73.682 cosine of negative 0.6265 plus I sine of negative 0.6265. And then if you try to convert to to rectangular form, just input this in your calculator. So square root of 73.682 angle of negative 0.6265. Okay, it's approximately equal to 6.951 minus 5.031 I. Okay. Or should be not 1, right? 33. Square root of 73.682 angle of negative 0.6265. 6.954 6.954 minus 5.033. Sorry. I think I inputted wrong values the first time. Okay, so this is the principal square root. Now, we will substitute this value in the formula here for our cosh. This is the formula for arc cosh of negative 7 plus 5i. Right? So that it's approximately equal to ln of negative 7 plus 5i plus this value of square root. Okay? The one that we got is this one. Right? So let's just copy. And then we combine this negative 7 plus 5i plus quantity 6.954 minus 5.0033i. Using your calculator, input negative 7 plus 5i plus 6.954 minus 5.033i. You will have, in decimal form, it's negative 0.046, then minus 0.033i. Then we get the ln of this complex number. Convert this to polar form. So x is negative 0.046, y is negative 0.033. So both x and y are negative. Therefore, the complex number is in quadrant 3. Okay, so finding the r, it's square root of x squared plus y squared. Square root of x negative 0.046 squared plus y is negative 0.033 squared. Input in your calcu, that's negative 0.046 squared plus negative 33 squared. Okay, it's approximately equal to 0.057. Then for the theta, so if the complex number is in quadrant 3, the formula for theta is arctan y over x minus pi. Substitute arctan of y is negative 0.033 over x, it's negative 0.046 minus pi. Use your calculator. Arctan of negative 0.033 over negative 0.046, 0.046 without exponent, minus pi. Okay, approximately negative 2.519 rad. Or you can just input this directly in your calculator. Negative 0.046 minus 0.003i, 0.33i, right? Okay, and then shift to 3, you will see you get the same r, approximately 0.057, and same theta, approximately negative 2.519. Okay, now we're ready to evaluate this ln. Copy. So the ln of this complex number is now equivalent to ln of r, 0.057 plus I theta, negative 2.519. So get the ln of 0.059, 7, sorry. It's approximately negative 2.865. Then minus 2.519i. So this is the principal value of the ln. Also, the principal value of the r-cosh already. So this is the final answer already for the principal value of r-cosh. Okay? You can also get the general value. General value of this ln is the same, negative 2.865 plus quantity negative 2.519, but with added 2 pi n times I. So this is the general value for n0 plus minus 1 plus minus 2 and so on. So this is the general value for the r-cosh. So this is the first set of answers, right? Remember, just like in the arc-sinh, r-cosh has also two sets of answers due to the presence of square root in the formula. So the value of square root that we got is the one when k is equal to 0. Now, we also get the value of the square root when we set k equal to 1 this time. So, copy the same formula, but we set k now equal to 1. Okay? So, therefore, square root of 23 minus 70i is, so same formula, square root of 73.682 angle of negative 1.253 plus 2 pi k, this time is 1, over 2. So, you have the square root of 73.682 angle. So, input this in your calculator. Negative 1.253, 253 plus 2 pi times 1, or simply 2 pi over 2. Approximately 2.515. So, angle 2.515. So, in polar trigonometric form, it's equal to square root of 73.682 cosine of 2.515 plus I sine of 2.515. In rectangular form, input this in your calculator. So, square root of 73.682 angle of 2.515. Approximately negative 6.953. 6.953 plus 5.033. Okay. 6.953 plus 5.033. There's an I forgot. Okay. Therefore, you will substitute this second value of square root in this formula again. Copy. This is the formula for arc cosh of negative 7 plus 5i. So you will have approximately equal to ln of negative 7 plus 5i plus this second value of square root, this one. Let's just copy. Okay. And then you input this in your calculator, you will combine. So negative 7 plus 5i plus negative 6.953 plus 5.033i. It is negative 13.953 plus 10.033i. Okay. Then you convert this to polar form, the complex number. X is negative 13.953. Y is 10.033. Negative x and positive y, therefore, the complex number is in quadrant 2, right? So r is the square root of x squared plus y squared. So square root of negative 13.953 square plus 10.03033 square. Square root of negative 13.953 square plus 10.033 square, approximately 17.186. Okay, and then for your theta, if it's in quadrant 2, theta is arctan y over x plus pi, right? So substitute the value arctan of y is 10.033 over x is negative 13.953 plus pi. Input arctan of 10.033 over negative 13.953 plus pi. Approximately 2.518. Or you can input this directly in your calculator. Negative 13.953 plus 10.033i. Then shift to 1. Sorry. Okay, this one. Shift to 3. So 17.186 approximately the value of r. And then the argument theta approximately 2.518. Therefore, the value of this ln is approximately equal to the ln of r, 17.186 plus I theta, 2.518. Get the ln of 17.186. It's approximately 2.844 plus 2.518i. Okay? So this is the principal value of the ln. Likewise, the principal value already of the arccosh. So this is the final answer for the principal value for arccosh. This is for the second set of answer. You can also get the general value of this ln approximately equal, so the same, 2.844 plus 2.518 plus 2 pi n. Okay, I general value for n0 plus minus 1 plus minus 2 and so on. So this is the final answer for the general value of the arccosh for the second set of answer. Okay, now let's check using your calculator. Let's show. So we start with this expression. So input the expression inside the square root first. So negative 7 plus 5i squared, then minus 1. Okay, get the square root of this. Input square root, shift abs of ans, and then angle of argument. So shift to 1 of the ans. So if we're getting the principal root, set k to 0, so you add 2 pi times 0 over 2. So this is the principal square root of this expression. Then you need to add negative 7 plus 5i. So plus quantity negative 7 plus 5i. Okay. So this is now the answer for the expression inside this ln. Then get the ln of this. So input ln, shift hype, adds, plus I shift to 1 ans equal. Okay, let's check. Okay, calculator, the answer in calculator is negative 2.844. We got negative 2.865. So there is a discrepancy due to approximation, due to rounding off in the steps of the solution, minus 2.518 versus minus 2.519 here in answer. But basically, they are approximately equal. They are near. Okay, next. How about for the second set of answer? Let's start again here. So input negative 7 plus 5i squared minus 1. Negative 7 plus 5i squared minus 1. Okay, then get the square root of the absolute value of the angle of argument. Shift to 1 of the ans. This time we set k to 1, so you should add 2 pi times 1 over 2. Okay, so this is the answer for the second square root. You add it again with negative 7 plus 5i, so plus quantity negative 7 plus 5i. So this is the answer for the expression inside the ln. Then get the ln of this. So ln of shift hype ans plus I shift to 1 argument of the ans. Okay, let's check for the second set of answers. We have, okay, for the real part, so this one is quite closer. 2.844 for the real part plus 2.518i. Okay, it's the closest answer that we got for the second set of answer for the Arcosh. Okay, they are approximately equal using our manual computation and the answer in the calculator up to 3 decimal place. Okay. Next, number 3. Let's have number 3. What if we have arctange of 5 minus 8i? Okay, for arctange of 5 minus 8i, let's check the formula again. Arctange of z is equal to 1 half ln of 1 plus z over 1 minus z. It is equal to 1 half ln of 1 plus z over 1 minus z. Wherein our z here is 5 minus 8i. Substitute the value of c, we have arctange of z, which is 5 minus 8i, is equal to 1 half ln of 1 plus z, which is 5 minus 8i, over 1 minus z, again, which is 5 minus 8i. So we simplify first the expression inside the ln. So you can combine 5 plus 1, that's 6, then minus 8i, over distribute this negative sign, 1 minus 5 plus 8i. So you can combine 1 minus 5 here, negative 4, right? Then you can factor out on the numerator and denominator 2. Factoring out the 2 on the numerator, you have 2 times 3 minus 4i. Factoring out the 2 in the denominator, you will have 2 times negative 2 plus 4i. Okay, so you can cancel out these 2. You will have 1 half ln of 3 minus 4i over negative 2 plus 4i. And then you divide. So you can divide it manually. 3 minus 4i divided by negative 2 plus 4i. Recall, you will multiply both numerator and denominator by the conjugate of the denominator. So what's the conjugate of the denominator, negative 2 plus 4i? Just copy the real part, negative 2, then change the sign of the imaginary part, positive 4i. Since it's positive, its opposite is negative 4i. Then just copy this on the denominator, negative 2 minus 4i. So you will multiply both numerator and denominator by the conjugate of the denominator, negative 2 minus 4i. So you will FOIL the numerator, multiply 3 times negative 2, negative 6, 3 times negative 4i, negative 12i, 4, negative 4i times negative 2, positive 8i, and then negative 4i times negative 4i, positive 16i squared, over, for the denominator, if you're multiplying complex number that are conjugate of each other, there's a shortcut formula. Just square the first term or the real part, negative 2. You square that, that becomes negative 2 squared, plus the square of the coefficient of the I, which is 4. So that will be 4 squared. And then we simplify further. We have 1 half ln of negative 6 combine negative 12i plus 8i, negative 4i. And then plus 16i square is negative 1. Therefore, this will be positive 16 times negative 1, negative 16. Over negative 2 square, that's 4, plus 4 square, 16. So you have 1 half ln. You can still combine negative 6 minus 16. Negative 22 minus 4i over 4 plus 16, 20. And then you divide negative 22 by 20. Then also negative 4i divide by 20. In lowest term, negative 22 over 20 is what? 11 over 10 minus, this is negative. 4i over 20, lowest term, it's 1 over 5. In decimal, negative 11 over 10 is negative 1.1. How about 1/5 in decimal? Negative 0.2i. Okay? And then, we evaluate the ln, right? Okay, so we convert the negative 1.1 minus 0.2i to polar form. So x is negative 1.1, y is negative 0.2. Okay, so what quadrant does the complex number lie in? We have negative x and negative y, both negative, that's why it should be in quadrant 3. Okay. For the value of r, we have square root of x squared plus y squared. So substitute x negative 1.1 square plus y negative 0.2 square. Use your calculator. Square root of negative 1.1 square. Sorry. There's no 3 plus negative 0.2 square. Okay, it's exactly square root of 5 over 2. Okay. How about for the theta? Formula for theta in quadrant 3 is arctan y over x minus pi. So arctan of y, negative 0.2 over x negative 1.1 minus pi. Input this in your calculator. Arctan of negative 0.2 over negative 1.1 minus pi. So this is approximately equal to negative 2.962 rad. Or if you want, you can just input this in your calcu, negative 1.1 minus 0.2 I. Then shift to 3. It is converted to polar form already. Square root of 5 over 2, same value for r. And theta, same value, negative 2.962. Okay, now, if we evaluate this ln, let's start with the ln. Okay, it's approximately equal to the ln of the r, square root of 5 over 2 plus I theta negative 2.962, or it's ln of square root of 5 over 2 minus 2.962I. Okay? But there is a 1/2 here. So we need to multiply this by 1/2. So if you put 1/2 here, you should also put 1/2 quantity, right? So distribute this 1/2, you will have ln of square root of 5 over 2 times 1/2 minus 2.962 over 2i. Or approximately, if you input this in your calcu, 1/2 ln of square root of 5 over 2, 0.056, right? Minus this one, 2.962 over 2, negative 1.481i. So this is the principal value of the arctangent. Okay, so this is the final answer already. We can also get the general value. Okay, so this expression is also the same as 1/2 quantity. We know the ln of this complex number is this one, right? Okay, we just need to change it by adding with this argument negative 1.296 what? 2 pi n, right? Okay. Then you distribute this 1/2, you will have 1/2 ln of square root of 5 over 2 plus negative 2.962 plus 2 pi n I over 2. So 1/2 ln of square root of 5 over 2 plus you can distribute this 2, divide negative 2.962 divide by 2 plus 2 pi n divide by 2 I. But we already know the value of this one. It's approximately 0.056 plus also this one, we already know the value, approximately negative 1.481. Okay, negative 1.481. And for this one, you can just cancel the 2. We just have pi n. Then times I. So this is the general value of the arctangent, arctange, inverse hyperbolic tangent, for n 0 plus minus 1 plus minus 2 and so on. Okay, so this is the final answer. Okay. Now you can check using your calculator. So you can start with this expression. Input the expression inside the ln first. So fraction, on the numerator you have 1 plus quantity 5 minus 8i over 1 minus quantity 5 minus 8i equal. Okay, you will see that we had the same answer for the quotient, right? Negative 11 over 10 minus 1/5 i, or in decimal, negative 1.1 minus 0.2 i. Now we get the ln. Okay? We get the ln of this. So ln of abs of the ans plus I argument. So shift to 1 of the ans. Okay, and then we need to multiply this by 1/2. So enclose this ln in the parentheses, then times 1/2. Okay, so we will check if we got the same answer. Okay, approximately 0.056 minus 1.481i. So we're correct based on the answer on the calculator up to 3 decimal place. Okay. So I think let's end this uh, live for now, and let's just continue next time the other three inverse hyperbolic functions, right? We only have solved the first three inverse hyperbolic functions, the arcsinch, arccosh, and arctanch. So for part 2 of this topic, inverse hyperbolic functions of complex number, we will solve examples on arccosec c, arcsec c, and arccoth c. So stay tuned for that. Okay, so please, if you haven't subscribed yet, you can subscribe to our YouTube channel, and don't forget to click the notification bell so that you will be updated whenever we have new uploaded videos or upcoming live tutorials. So I hope you learned something from this video, and don't forget, if you want to watch all the previous videos all about this series, Advanced Engineering Mathematics, the links of the videos are just in the description, as well as the main playlist, Advanced Engineering Mathematics. I will also link it in the description. So good luck and God bless to your studies. See you on my next live. Bye-bye.